All right. Hey chemists, this is going to be a video on empirical and molecular formulas. So in general, if I ever ask, or when you are asked, what is the empirical formula? What I'm really asking, or what is being asked, is give me the chemical formula. So like H2O and C3H8 and ZnCl2, like the empirical formula lab. Please write this at the top of your notes there, so you know if you see questions that are like, what is the empirical formula? You know what you're trying to find at the end. You're trying to find and write chemical formulas like this. We've already determined now, speaking of empirical formulas, we've already determined the percent composition of elements and compounds from their formulas. So for example, H2O, if I have a mole of H2O, that's 2 grams of H, 16 grams of O, and mathematically, that's 11% H, and 89% O. We have been able to follow the steps to get percent composition of elements in a compound. I want to let you know for any given compound, those percentages are constant. So, formulas that we typically work with are formulas that have the simplest whole number ratio of atoms of elements in the compound. These simplest ratio formulas that we get from these percent compositions are known as empirical formulas. And so the actual definition of empirical, if you were to look it up, what it means is experimentally determined. Sorry, I got a little typo there. That means experimentally determined. And we experimentally determined the formula of zinc chloride, like the zinc chloride lab. We did all the math, and we got 2Cl for every 1 Zn, and so that gave us ZnCl2. That's what we were supposed to get from that lab. H2O and C3H8 are examples of empirical formulas because the ratios, like 2 to 1, of elements in the compound are in their simplest form. That is, cannot be divided further. So like H2O, there's 2 H's and 1 O. So there's 2 moles of H for every 1 mole of O. Or 2 atoms of H for every 1 atom of O. Or we had the zinc chloride. Like we said before, there were 2 atoms of Cl for every 1 atom of Zn. And that gave us an empirical formula of ZnCl2. So those are examples of empirical formula. They cannot be divided further. Or even if I do C3H8, some numbers that are not so 2 to 1-y, that'd be 8 atoms of H for every 3 atoms of C. And that cannot be divided further. 8 doesn't go into 3 and 3 doesn't go into 8. So that is empirical formulas. Now we're going to move into molecular formulas. Look at this data table here. I have examples of empirical formulas and their respective molecular formulas. So here's empirical formula CH. That means that there's 1 H for every 1 C. It has a molar mass of 13. If I make it or find a molecular formula of it, it could be C2H2, and that has a molar mass of 26. Or if I make a molecular formula of CH into C6H6, that has a molar mass of 78. How does the molar mass compare of the molecular formula to the empirical formula? Well, it's multiplied by a whole number. To get to 78 from 13, I multiply by 6. I also multiply my formula by 6. So CH becomes C6H6. That's multiplied by a factor of 6. From the table and particle diagrams below, what can we deduce about the difference between empirical formulas and molecular formulas? Let's say this was CH, so this is C, and let's say the shaded circle is H. This would be CH. This is an empirical formula. But look at this other formula. This looks like it has 2 C's, 2 H's. This is what we're going to be calling a molecular formula. To go from empirical to molecular, it looks like I'm multiplying by some whole number. This one is 2. It looks like to go from empirical to molecular, it looks like I multiply my particle diagram by 2. So molecular formulas then, to write this down, are a whole number times larger than empirical. So for this one, it was 2. So the difference between something like CH and C6H6, to go from CH to C6H6, I have to multiply by 6. The multiple is 6. So the molecular formula of a compound is a simple whole number multiple of the empirical formula. Okay? So that is empirical and molecular formulas. I'm going to now end this video with talking about how do I get empirical formulas. And we're going to learn to follow these 4 steps. Working backwards, if we are given the percent composition of the elements in a compound, we can determine the empirical formula. So let's do this through an example. There are 4 steps we're going to follow. A compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. What is the empirical formula? The simplest ratio. The simplest ratio. That's what it's asking of atoms. So here are the steps. Assume that we have 100 grams and convert the percentages to mass in grams. So we'll do step 1. Step 1 says I take my 25.9% nitrogen and I make it 25.9 grams nitrogen. It says I take my 74.1% oxygen and I turn it into 74.1 grams oxygen. That's my first step. My percentages become automatically grams. My second step here says convert the mass of each element to moles. And we do that by dividing by molar mass. And for elements, we get that from the periodic table. So for number 2, I'm going to convert the 25.9 grams of nitrogen to moles by dividing by its molar mass, which is about 14 grams per mole. So you're going to have to trust me that the molar mass of nitrogen is 14. And so I get 1.85 moles of nitrogen. I'll do the same thing for oxygen. I got 74.1 grams of oxygen. I will divide by its molar mass, which is approximately 16 grams per mole. I'll highlight that. Trust that that is the molar mass of oxygen. And I get 4.63 moles of oxygen. So now I have a compound that for every 1.85 moles of nitrogen, there are 4.63 moles of oxygen. I got to figure out a formula. So let's do our third step. The third step is divide each mole value by the smallest number of moles calculated. Between 1.85 and 4.63, I am going to choose 1.85 as my lowest moles. It is my lowest moles. And so I'm going to divide both these numbers by 1.85. So I have 1.85 moles of N. I'm going to divide it by 1.85. I have 4.63 moles of O. I'm going to divide that by 1.85. If I do this, I will get 1N and I will get 2.5 O. And so in the end here now, I have to try and either round to the nearest whole number or find whole number ratio. Maybe like as an improper fraction. And we've done this before. So I have 2.5 moles of O for every 1 mole of N, or 2.5 atoms of O for every 1 atom of N. Now, 2.5 is not a proper improper fraction. I need whole numbers. How can I turn 2.5 over 1 into an improper fraction, or a ratio that gives me whole numbers? Well, 2.5 over 1 is the same thing as 5 over 2. That is 5 atoms of O for every 2 atoms of N. And now I have a ratio of the atoms that I could get whole numbers to, and I could write my empirical formula. That means my empirical formula will then be N2O5, or you could write it as O5N2. I don't mind which way. This would be the correct answer that we're trying to find. And I'm going to end this video with, what if I had even simpler numbers? What if I found out that I had 2 moles of O for every 1 mole of N? Then my empirical formula would be NO2. So like, what if? And I'm just showing you that because what if the numbers are, I don't have to worry about doing this improper fraction business. If it's about 2 to 1 or 3 to 1, then I turn those numbers into subscripts. Alrighty, that is the end for this video lecture. We're going to clarify more in class. If you have any specific questions, make sure you ask them in class.